Good afternoon, everyone. Welcome back. The first talker this afternoon is Professor Chao from Chinese Academy of Science. His presentation title is Adaptive Regularized Neuron Physics for Nonconvex Optimization, Optimal Global Complexity and Quadratic Local Convergence. Let's welcome him.
Okay. Okay. Thank you. Sorry for the. Okay. Anyway, thank you very much for the invitation to attend this conference. Today, I'm want to present our new recent work on the very old topic, which is algorithm for the non-convex optimization. You can see from title, we are mainly focused on two things. One is a so-called optimal global complexity. This is typically interested by the industry and researchers in AI or machine learning community. And another topic is another one is a so-called quadratic local convergence, which is naturally come from the Newton algorithm. So basically, you will see we want to achieve these two main goals in this project. So I'm Chao from the Institute of the Applied Math, AMSS, Chinese Academic Sciences. This project is a joint project with a couple of students and colleagues from the Tsinghua University. The Zhou Yuhao is already graduated from the Tsinghua University CS department, and whose supervisor is Zhu Jun in Tsinghua University, and also Xu Jingtao already is a former student of the Tsinghua Math department, and Li Bingru is current student in the PhD student in the Tsinghua CS department, and Chen Longbao is exactly this center in Tsinghua. And you can find the paper in the archive, and although we have the code available, which if you are interested in. So old topic, the Newton method is today's agenda. So very simple optimization problem which we considered is a non-convex one. We are optimize a smooth but maybe non-convex function, and we want to find the minimize in the whole space. This is a very classical optimization problem in the literature, and of course we may have to make some assumption. One is a smooth, the function object function is smooth, and addition to that we have the so-called LH Lipschitz continuous for the Hessian. Although we need the level set boundedness of the assumption, but I think this is a quite standard assumption for this kind of study. And the goal is find, of course, because this is a non-convex optimization, it's very hard to find the global optimal solution. So today our goal is to find so-called epsilon stationary point, which because this function is smooth, so you can compute the gradient and calculate the gradient Hessian, so a gradient norm, and we use the L2 norm here. We require this norm to be smaller certain level, which is called epsilon stationary. If epsilon is 0, it of course is stationary. But if it's stationary, does not mean it is any local optimal or global optimal, because we are considered the non-convex case. And the Newton method is very classical, and you can find any textbook in the whatever the optimization or application mathematics numerical algorithm. You will find out this method is very standard, which you at current stage you want to find out a Newton step by solving. I like this quadratic form. Of course we know you can solve the Newton equation, which is equivalent to this minimize problem, and approximately. So this is the basically Newton method. But the globalized, everyone knows Newton method is a so-called local method, and the main topic and the main difficulty for this method to success is the globalization. So there are a bunch of globalization methods exist in the literature. For example, here I list 3 of them. One is so-called damped Newton, because we know the we can use or other aka line search, which means you if you can influence the direction you find out, the Newton direction is a distant direction. You can follow this this direction and go a little bit further with a step length. Then under some suitable condition, you can show the Newton method will the damped Newton method will global converge to the stationary. Another type one is a famous trust region method, which means basically you believe at a certain level or certain region the object function can be well approximated by the so-called quadratic model, and you use this quadratic model to surrogate or replace the original model and find out the optimal solution of the quadratic model, and certain suitable rule to adjust this kind of radius is required in the trust region. And the third one is a little bit interesting, which is so-called the qubit regularization, and proposed by the Nestov and Polya in 2006. They say maybe the quadratic model is not so nice. So a quadratic model is nice, but we still need to justify this kind of region. So what about use the qubit? Use quadratic model. Use qubit model. So here he added the so-called qubit regularization term to the quadratic model, and indeed they show this model will global converge. And they indeed have very good global complexity, which is the optimal, so-called optimal global complexity. But they're a little bit, they're a bad thing or disadvantage is it's very hard to solve this kind of quadratic subproblem, even for very simple one. But in the practice, people usually use other kind of method. For example, they even use the trust region and the damped Newton to solve this subproblem. So this is a situation for the qubit regularization. It have very good theoretical guarantee for the global complexity, but although the local convergence, but the subproblem is very difficult to solve. So today we are consider another type of method, so-called regularized Newton method. The regularized Newton method is very simple or have very simple form, which is solve this kind of Newton equation. If we ignore the rho k, it's exactly Newton equation we see in the classical Newton method. But here, because we add the rho k and use this parameter rho k under some suitable condition, you can see actually they have other names, so-called Levenberg-McQuarrie method or quadratic regularization. This method have simpler subproblem compared with the qubit model, because this is just to solve the linear system, which is a very old and standard topic in the numerical algebra. And another one, although it can, one of the very efficient methods, so-called the conjugate gradient method, because it's, you can use conjugate gradient. Then if for very large system, you do not need to even know the exact Hessian, what the Hessian is. The only thing you need is a Hessian-vector product. If you can perform this kind of operation, then you can use the CG method to solve the subproblem. So the benefit is this method have very simple subproblem and easy to implement, and although it have very good performance in the practical. But our focus is another way, which is what about the global complexity of this method and the also so-called oracle complexity. And another one is, because this is the Newton method, so what about the local convergence rate? this is the main topic, as I mentioned before. So there are gaps in the study of this kind of so-called regularized Newton method. One challenge is anybody can design a so-called regularized Newton method simultaneously to achieve two goals. One is optimal global complexity, which is a so-called capital epsilon negative 1.5 complexity. We know the cubic Newton method can achieve this global complexity, but the subproblem is hard to solve. But we want to ask whether the regular Newton method can achieve this one. And another one is, if indeed you have some kind of good property for the Hessian, can the algorithm achieve the so-called quadratic local convergence, which is indeed the good property of the Newton method, and additionally without knowing some the so-called Hessian Lipschitz constant. Previous study about this type of algorithm often face a trade-off. One is if you want good global convergence, global complexity, you may sacrifice the local speed. If you want fast local convergence rate, you cannot guarantee the optimal for the global complexity. This is some kind of a trade-off. And our approach in we will design or propose adapted way regularized Newton method to achieve this two, and you will see this is this algorithm will be a parameter free. You do not need to turn in some super parameter to get the algorithm performed well. Yeah. So before I go into my algorithm, we want to introduce some current study about this topic. Compared to the already known regularized Newton method for the non-convex optimization, there are a bunch of them. You can see there are first one is get by the student of the Stephen Boyd and Stephen Wright and his student. The algorithm they propose indeed can achieve the so-called optimal global complexity, but the local convergence rate is only linear. And although they need some kind of additional effort to achieve this kind of global complexity, which is at each step you should specific to know what is the tolerance of the current stage. And another work, maybe another type of work is given by the Garden. So they sacrifice a little bit about the global complexity. They only they have additional log term here, log 1 over epsilon, and this is a suboptimal complexity, global complexity, but they can achieve a little bit better local convergence rate, which is 1.5. And unfortunately, they have to know the exact the minima Hessian, the minima eigenvalue of the current Hessian. So it requires eigen evaluations, which is very costly in the large problems. And in our work, we propose two kind of adaptive way. Both can achieve the so-called optimal, the quadratic local convergence rate. And one of them is suboptimal, but still better than the Garden's one, which is a log term, which is much smaller than the log term. And another one is we can achieve the optimal global complexity and also achieve the local convergence rate. So this is what I already say. Another one is I can skip this one. So for the global complexity of the regularized Newton method, all the study have this kind of key step. We want to estimate the function value decreasing at each step from the k plus 1 to the xk. how much of the function value decreasing. And usually we will come out this kind of inequality. Here the gk is the current norm of the gradient, and we want it's a very naive idea. If you want to achieve the so-called optimal Gruber complexity, the automatic way is you can choose, because the rho k can be chosen by us, by you. So you can choose, for example, the rho k as proportion to the so-called epsilon 1/1.5. Then you will obtain the so-called optimal Gruber complexity automatically. Very easy. If you, of course, you want to, we have to choose the gk plus 1. And this is a better choice is so-called rho k can be chosen as a proportion to the epsilon 1/2. This is exactly the Stephen Wright and his student done, and they say if the gk plus 1 is bigger than epsilon, then we can choose this rho k. Then we can obtain the group optimal Gruber complexity. Otherwise, which means you already get the epsilon solution, so you are done. The job is done. So this is a very simple idea of this Gruber complexity. But turn to the local convergence, a local convergence rate. The key is to show eventually the Newton step will taken, which means this kind of inequality will be solved, which means if you can see, basically is the equation, which means the rho k should be proportional to the gk. Gk is the exact norm of the current gradient. So, for example, actually, if you choose the previous one, which is the optimal Gruber complexity, for this kind of simple quadratic strong, strong convex function, you will see it's automatically leads to linear converge. You can see it will, for this iteration, it will become linear. So, which means there have some kind of contradiction both from the Gruber one and the local convergence rate. If you use this kind of simple idea, you will never get the good quadratic local convergence rate. Okay, so another way, maybe this is too simple to choose rho k become 1 epsilon 1/2. Maybe we have better choice. Is indeed some of the researchers have suggest we can choose the rho k proportion to square root of gk. This is another choice, but you, for the Gruber complexity, we have to, for example, like this picture. Typically, this is a very typical picture for solving the non-convex optimization. For algorithms, at the beginning, you will see this kind of up and down, and it will not perform very fastly, and suddenly at a certain level it will drop very quickly. So they have two kind of decreasing. One is sufficient decreasing and the insufficient decreasing. For the sufficient decreasing, this means you have this up and down, and otherwise you will decreasing very fast. Then a very simple idea is if a sufficient decreasing occurs, then at least they will okay. Actually, they count this kind of sufficient decrease at this kind of level. At every capital O log 1 over epsilon step, they will happen at least once the sufficient decreasing. Then they can show the suboptimal Gruber complexity. Actually, we study their method counting more carefully. We found that actually there is a log term and not the log 1 over epsilon. They are overestimate. Okay, so this is another way. I just want to but turn to the local convergence. If we choose this guy, they will give you, we do the numerical test, we found if we use we use this choice, we only can get the linear conversion rate. It will not become the quadratic local conversion rate. Again, use this simple example. So this is a trade-off. Optimal global rate requires larger value of the rho k, which is proportional to the square root of gk. A quadratic local rate requires smaller value of the rho k. So basically, it's very hard to at the beginning for us to find out this this good rho k. So we do the following. We can ideally choose the rho k as proportion to the square root gk times the delta k, which delta k indicate whether it is belong to the this bad region or the good region. If it's already in the good region, which means we can use the smaller value of the rho k. If it's outside this one, we can use a larger one. This is the basic idea. But the thing is, the difficult thing is, we cannot have any information before we know where the solution is. So this is basically the difficulty we face. So the strategy we use is how to distinguish global and the local phase. This is the main. The key insight is the following: if the algorithm are already become quadratic converge or already very close to the solution, the Newton conversion rate will become quadratic. You will observe this kind of phenomenon, which is the gk, the norm of the gradient, decreasing rapidly and monotonically. You can see from the picture it will not happen the up and down. So we can use this kind of a thing to use this very simple insight to decide the following way. We use the delta k become minimum 1 and this ratio. If it's not close to 0, it becomes 1, so it means it's outside the quadratic convergence region. Otherwise, it will become the quadratic region. So basically, this is a very simple idea. We just doing that way. A little bit of careful design. We can use the theta here. This is the power 1. We do the numerical test. You can see if the theta close to the 1, it will more like the quadratic converge. For the global convergence, we have to handle this kind of sharp decreasing. This is a will give you suboptimal or optimal global complexity. I will not go into the details. I think this is not important. But finally, if we want to get the optimal global complexity, compare with the previous one, this one will give you the suboptimal, which is the log-log. Here we use the gk. Gk is the current iteration gradient. If you indeed you want to obtain the optimal global complexity, you have to use this epsilon k, which is what is epsilon k? Epsilon k is until now the smallest value of the gradient norm. So you will store all the no need to store all, but you need to use the previous information of the gradient. So basically, this is a choice, and if you use this choice and without although we design a mechanism to estimation the Hessian Lipschitz constant, this is a not big deal, and then we can use Newton CG to design a proper Newton CG method to solve this subproblem, and then a little bit complicated, but I will skip it. And this is a Newton CG. I will not go into the details. So finally, this is a convergence result. We have some assumption. We assume the function is smooth, and the Hessian is, as I mentioned, is a Lipschitz continuous. and the level set is bounded. Then for the regularization choice 1, which bases the GK, current information of the gradient, then we use this choice, you will get this global complexity, which is suboptimal because we indeed have the log term. If you indeed want to have the optimal global complexity, you need to more information about the gradient. You need to use the previous information of the gradient and use this epsilon k. Then you will get the optimal complexity. And the local convergence, both of choice will give you, if the Hessian at the solution point is positive definite, then you will have a quadratic convergence rate. Okay, so this is a whole algorithm. So for the oracle complexity, for each iteration, the function evaluation is at most 2 mx plus 1. What is mx? In the algorithm, we design a mechanism to do the line search. Usually the mx is 1. We set this number is 1 in the iteration. So basically, at most 2, 4. Yeah, function evaluation for the each iteration is 4. Gradient evaluation at most is 2. The Hessian-vector product is this number. Okay, this is the same as a CG. The total complexity for the epsilon k based algorithm is second order oracle core is this number, which is the iteration. Already match the so-called lower bound of the second order method up to a constant. Up to this one is independent of the dimension. This comes from because we do not assume we know the Lipschitz constant, so we need some effort to estimate the Lipschitz constant. And although this is the optimal dependent for the, this one, the LH is power 1/2, and the Hessian vector product is this number. The capital O tilde epsilon 1 over -7 divided 4, which also matches the lower bound for the second order method. So basically, if you use this choice from the oracle complexity, it already be the optimal. Okay, next, some of numerical tests. We first present some numerical tests for the famous so-called the Curtis benchmark. This is around, there have a bunch of non-convex optimization problem, non-convex, and we collect the larger size one, which is about 240 problems, which dimension is larger than 100. And we use the machine to do, and we compare with the state-of-the-art method to this in this test. One is a so-called CAT, is a trust region method, which is I think is the most efficient trust region method to solve this non-convex optimization. And another one is N2 curve. So this is a regularized Newton method, proposed by the Garden. As I mentioned, there are arguments for the global convergence. This is suboptimal, and the local convergence rate is 1/2. So this is not optimal one. And this guy is the Kubernetes regularized Newton method. Indeed, it uses trust region to solve the subproblem. So they have some problem about the subproblem solving. And these two are our algorithm, proposed algorithm. The G one means we use current iteration gradient, and the epsilon one use previous all the information at the current stage. Okay. So this is a comparison with success rate, which means giving you time budget, how many counting the problem you can solve at the level. So you can see not very clear, but basically we are same with the regularized Newton method, cubic Newton method. So this is a more clear table is following. We use a shift geometry mean to measure the different methods. You can see the best for almost all the algorithms. The best one is this one, not the one we use for to obtain the global optimal global complexity. This is because for this, if you choose this epsilon, for the subproblem you will have more effort to solve the subproblem more accurately, and we recommend this one, the G one. Okay, what I want to say is the following. The time is very fast, and I want to emphasize is the following. This guy is this one is a cubic Newton method, and you can see the Hessian evaluation is much more Hessian evaluations. This is because they use the trust region method to solve the subproblems. They need more Hessian evaluations. Basically, we are the same success rate compared with regularized Newton, but less effort in the subproblem solving. Okay, another numerical one is a very popular one, the so-called physical informed neural network training problem. Basically, people want to use the neural network to train the PDE solutions. Basically, we have this kind of form at some region, and you have a differential operator and a boundary condition or initial condition, and people usually use the pins, so-called pins, to approximate the solution of the PDEs. And what they use a full connect neural network, so-called the F theta. The width is 203 hidden layers. Later you will see the structure, and the parameter is theta is a parameter we want to optimize in the training stage. So this is how many 2100 parameters, and not very but in double precision, not very large but still challenge. They train this so-called residue-based loss. This is a object function they want to minimize. Basically, they are non-convex, highly non-convex problem. This is the structure they use. So where we are, we will ignore all the. This is borrowed from others. This is a stage we face the training stage. So what is the challenge about this problem? This problem, the challenge is a high precision solution needed, which means the loss function need to be nearly zero, is much smaller, is close to the zero as possible to obtain even a low quality solution. And another one is the non-convexity and the poor conditioning. To make this kind of training task is very difficult. This is already observed by a bunch of people. And people here we try to do the numerical test in 3 problems: convention, reaction, and wave problem. Follows the training strategy proposed and compare with them. Because this is very hard problem, so none of the algorithm will succeed if you only use one of them. For example, people usually use Adam at the first stage. After train a little bit, and then use some kind of second-order method, limited memory BFGS, train a little bit, and it will stuck in some level, and then they use kind of another second-order method to train again. So basically, this is the strategy they use. And for comparison, we compare with so-called NCG, which is simply a non-convex Newton CG method without any Gruber convergence guarantees and proposed by the authors. And we use this GPU to train this model. Yeah, this is a conversion problem result. You can see, this is the time, and we first trained with one 11K Adam step, and then 1.5K Newton limited memory BFGS, and then train use whatever their algorithm without the Newton CG algorithm, without the guarantees, and our algorithm with 7.5 hours. And you can see this is the performance of ours, and this is their algorithm. So our algorithm still perform better. Yeah, and the same story about the reaction problem and the wave problem. Wave problem is a little bit difficult. We train even after the Adam and the limit memory, we train 18 hours. And this is a report. So at the training loss, you can see we can achieve very high, nearly zero training loss, and the test error is still low, which is but ours is better, the best, but still low. You can see the test error is -5, and for the even worse for the wave problem, and but the main thing I want to emphasize is our algorithm, because we do not need to store the whole full Hessian, which is much memory use less memory. For example, if you want to store the whole Hessian about the wave problem, you need this bunch of memory, the nearly 50 gigabytes. But our algorithm, the peak GPU memory, only have 10 gigabytes. So this is a memory. I can see that we want to see the memory-friendly algorithm, second-order algorithm. Okay, so yeah, for the summary, we propose adapting regular Newton CG method. The key observation or thing is this can achieve both Gruber optimal Gruber complexity and the local quadratic rate. It have theoretical guarantees and parameter free. We do not need to know any information about the Hessian Lipschitz and even the tolerance epsilon. And the numerical test say it's competitive with the state-of-the-art algorithm based on the benchmark. And for the challenge problem, for example, like the pins, it performs well. And memory efficiency is another benefit for the large scale problem. Okay, thank you.